old AV gods then. Let's see if that works. Ah, that's better. Okay, come on. Do we have? Right. Okay. Dismiss. Right, go. Wheel of Death. Come on. Okay, now let's find where this one is. DeepRacer 101, here we go, right, finally. Okay, right, so what this session is going to cover is a very quick introduction into what reinforcement learning is, followed by an introduction into how that is relevant for AWS DeepRacer. Okay, so before I begin, how many people would say they have some understanding or some knowledge about what machine learning or artificial intelligence is? Okay, a few of you. And how many of you have some understanding or some knowledge of reinforcement learning? Wow, this is good. Okay, so less of you, but still a few. Right, so hopefully the first section will, for those that know something, will help solidify that knowledge. For those that don't know, will hopefully help you understand how this fits into the broader AI machine learning landscape. And then we'll move on to how that's relevant for DeepRacer and how you can apply that knowledge when we create our first model, okay? So this is the same deck for people who watched online, the same deck we use, so you can always go back to the recording on Twitch if you want to. So when we look at machine learning, there are broadly these categories. We have supervised learning, unsupervised learning, and reinforcement learning. Okay, you're probably more familiar with the term supervised learning and unsupervised learning, where supervised learning is where you have a data set that's labeled. So for example, if you've got a collection of pictures, they might be labeled as to what the picture is. So you might have a collection of pictures that says this is a cat, this is a dog. And so we have what we call a ground truth of that data. And you will apply an algorithm, and there are different algorithms that fit into supervised learning that will typically allow you to do something with that data. So for example, it might be a classification algorithm that allows you to, based on an image, and that data that's labeled, that ground truth, allows you to say, I think this picture is a cat or a dog. Unsupervised learning is where you don't have the ground truth, okay? Where you've got a collection or a corpus of documents, and you have a feeling that there is some groupings or something in there that some insights you want to get from that collection of data. So in this instance, it might be, for example, a grouping of documents into certain categories. So you don't have that as ground truth, but you've got algorithms that will help you make meaning from that data. But what if you don't have a labeled set of data, okay? And what if you want to do something that's maybe perhaps interesting from the point of view of being sophisticated and mimicking an activity that a human would typically like to do? So we like to kind of plot how these work using this chart. So the amount of data you require on the bottom is larger as you go to the right, and then the sophistication, what we mean by sophistication is how good a job is it based on what a human could do, and how much value does this job do from a human perspective. Okay, so when you've got supervised learning, okay, you need lots of data and an algorithm, but typically it allows you to have a high degree of precision. Throw a picture of an object and it will tell you what that object is. Okay, with unsupervised learning, you need less data, But typically the kind of level of sophistication is something that a human could probably do, but it's just time consuming, right? So I've got, 100 documents. I could probably, alphabetize them, or I could probably find that these documents are legal documents, those documents are mortgage applications, but, it's time consuming. And so the level of sophistication isn't as high. Okay, and where reinforcement learning sits is where you want to have a high degree of sophistication, but you don't have any data, or you have very little data, or very poor quality data. Okay, so this is how you can kind of imagine the relationship between the sophistication and the amount of data you have, as to how these all fit together. And obviously you don't really want to be in a situation where you've got lots of data and you want a low sophistication, which is why we've got the X there, right? Because why would you do that? Yeah, it doesn't add any value to you. And the way we like to think of this, okay, is when you were small and you learnt to ride a bicycle, your parents were encouraging you to learn to ride the bicycle. So you, in this instance, okay, were what we call an agent. And you wanted to learn how to go from A to B. And you knew that when you got on the bicycle, I had some pedals that I could move. I could move them faster or slower. I had some brakes, and I could move the handlebar to change direction. And so my parents were encouraging me, and they were trying to tell me how this would work. I, as the agent, would actually then try and do stuff. And whilst I was learning to ride my bike, I would have certain situations where I would fall and hurt myself. And sometimes I'd actually get brief moments where actually I was powering myself and it felt good. Time as I got the idea of the balance and the pedaling and the steering together, I would actually then be able to use that to go from A to B. Okay, so we like to think that as kind of like one of the ways of you can imagine how reinforcement learning is, in our day-to-day lives. And so in that context, okay, we have this concept of an agent. Okay, and the agent, in this instance for the bike, it was the person who was riding the bike. In DeepRacer, it's the car. And they can do a number of actions. So if I'm learning to ride a bicycle, I can steer, I can brake, I can pedal faster. And when I'm cycling, I interact with the environment. Okay, so I'm in a road, I'm in a park. Hope there's no cars, depending on how good a child you are, I guess. And then as you are doing that, what happens, okay, is you are evaluating the change in your environment. So as you cycle closer towards that tree, you're taking on board the fact that I'm getting close to that tree. And then that process begins over and over again. Okay, and the fact that you evaluating the new state, you're being rewarded because you've stayed on two wheels, not fallen over. So you think, okay, whatever I did then was good, I'll keep doing it more. Whereas if I try to turn too fast, go too quickly, I might fall over and I won't do that again next time. And this really is kind of like the underpinning mechanics of all reinforcement learning. Okay, and so when we see this being applied in real life, okay, because one of the things that I get asked a lot is that this is all good, Rick, okay, DeepRacer is fun, but how would you apply this in real life, right? What's the point? The point is that there are lots of different use cases where reinforcement learning is actually really interesting and can be a very viable approach. So typically where you've got uncertain and very dynamic and changing environments where you want the model to continuously learn and update. So I've got three very quick examples. The first one is recommender systems. Okay, so we use these a lot in Amazon, right? You go on the website, you look at products, you want to make sure that you get the right products recommended to you. And in this instance, okay, the agent is the recommender, the one that's finding the best match for you. The action is to choose among all the different items in your catalog. The state is whether you as a consumer are liking those products, clicking on them to see them in more information. And then the reward ultimately is do you convert into a sale? And that process can iterate quickly, and then it allows you to have a much better, more accurate recommender system, which effectively trains itself because it's learning as it's doing the process. The second one is energy systems. So if you imagine heating and cooling a building like this, any building, there's lots of parameters, okay? How many floors, the floor layout, the season you're in, the optimum temperature for the time of day, whether you've got more of one type of person in one area. All these are very complicated variables, okay? It's a very complex environment. So in this instance, the agent would be the control systems that control the temperature, pressure, and they would allow you to turn off and on various devices, which is the action. The state is the temperature or pressure a specific room is in. And the reward ultimately is no complaints from, the people that it's either too hot or too cold. And then perhaps the most common use of reinforcement learning is robotics, where you have an agent, in this instance a robotic arm, that can do certain actions like grip or move certain angles. And it takes the state through a sensor like a camera, and then the reward is what you want it to do. So does it want to pick up an object or move an item from A to B, that kind of thing. Okay. So you can see these are all kind of use cases for reinforcement learning. So that's all good. That's as far as we're going to cover theory today. Okay. So now we're going to cover sort of DeepRacer. I'm going to skip through some of these slides because we're all here. We all know why we're here. We all like DeepRacer. We all know what DeepRacer is. Okay. It's a car which you've seen upstairs. It's a simulator which I'm going to talk you through and walk you through in a minute. But it's also a racing league. Okay. It's a racing league that's physical at summits which actually have now finished, although we've got the one at reInvent. But I guess the really interesting one for us here in this room is the virtual one, where we create a model, we submit it to a virtual league, and hopefully we get good enough time to be winner. Okay, so that's that there. Okay, so I've covered these terms from riding a bike, but from the point of view of DeepRacer, the agent is the car. You're interacting. Sorry, the actions it can take are basically the speed it goes and the steering angle. There's no braking in this car, so just like my driving, pretty much. It's interacting with the racetrack, which we've got upstairs, and whilst it's doing that, it's being rewarded. Okay, so was that a good manoeuvre? Or was that a bad manoeuvre? And whilst it's doing that, once it goes from one state to another state, it is capturing whether that was a good move or a bad move. And then a concept of an episode is when the car is learning to go around the track, we measure either a complete a lap or when the car leaves the field. So when it goes off the track, we call that the end of the episode. Okay, so these are terms I'm going to start talking about. And the way this learns, okay, is when the car first starts, it knows nothing, okay? It has a reward function, which we're going to come to in a bit, but it has got no learning, so it is in the wild, okay? So what will happen is it will take an action. It's got an action space, which is either go left, straight on, right, or a certain speed. And when it does that, okay, it will go into a new state. So it's the S+1, right? So I was here, I'm now here, that's the next state. Okay, in the process of doing that, I will be rewarded. Now that might be a very small reward, it might be a very large reward, okay? And then the agent will then repeat that over and over again, and we call that an iteration, okay? And that is used to train a SageMaker model to create a policy function, which is the bit on the right-hand side, on the bottom there. And the policy function maps what it sees to the action space. So left, straightforward, right, faster, slower. Okay. But just like on a bicycle, okay, just because you know that you can go left, right, straight on, cycle faster, doesn't necessarily mean it's the best move, right? So how do you know that when I'm cycling around or when I'm driving around a racetrack, how do you know that the racing line is the best line or not? Okay, you do that through experience, through being rewarded over time. So as this is going through, the total cumulative reward is then used to create a value function. So we now know what to do in a specific state, but we also now know through the value function what the highest reward for a particular move is likely to be. And that's really important because when we come to creating the reward function, we need to make sure that we optimize that to make sure that our car is doing the best to get the best time around the lap. Right, that's a lot of me talking. Any questions?
What comes in the state?
So the state is so the state is image, I believe. Is that right, Lyndon? It's 15 frames, 15 images per second.
State is partly the image. There's also in the virtual environment will give you context about where the car is on track, whether it's waypoints, whether it's.
Yeah, it's a good point actually. So we're going to cover. So there's a distinction between the real physical drive car and then the training. In the simulator, there are parameters that we feed into the reward function which you can use to help you with the state, but the real actual state is what the car can see through the camera. And the car is operating at 15 frames per second, so it means that typically every picture, so 1/15th of a second, it will take a picture. It will then use the additional parameters, as Lyndon said, that we provide within the virtual simulator, and you can use that in your reward function. But we're going to come to that, so hopefully that will become clearer.
Maybe coming to this as well, presumably it's pretty technically constrained.
Yes.
That you have to do it with reinforcement learning, because that's a hack.
Yeah. Well, so in the because we provide a console, the only three, we're going to come to this, so I can cover it now. There are three things you could do. The first one is you create the action space, right? So we give you some flexibility on the action space. Typically, it's the degrees of turning, the granularity of that, and then the same thing for speed, right? The second thing is the reward function. So how do you reward a particular behavior? And then the final one is when you're training the model, how do you tune the hyperparameters? Okay, so those are the three kind of things you've got control over, but you don't have control over the algorithms or anything like that yet. Yeah. Okay.
So how many laps do you have to do before the model starts to stabilise with that feedback loop?
It depends. Is the answer? I mean, we'll come to that when we're doing it, but. Initially, when we're training, it's very much in what's explore mode, and so it's pretty much random. Okay, depending on how good those three things are I just talked about, your reward function, the action space, and the hyperparameter tuning, you might end up in explore space for quite some time, right? And your car will look like it's not doing particularly well. Sometimes, though, if you use like the default ones, you can within maybe 30 minutes, 40 minutes, you can actually get some stability. So it all depends on those three things.
So in the physical races, would you have trained it in the virtual?
So you can only do it in the virtual first. You can't go straight to the physical.
Okay, so you train your AI in the virtual environment, and then you apply it to the physical environment.
So I've got the workflow coming up, so it will come. Yeah. Okay, that's right. Yeah, that's cool. It's cool. I asked the question. So what I want to quickly talk about now is that people who are familiar with AI in autonomous driving. Okay, there was a project called the Donkey Car Project, which we talked about earlier with some people here, and I also kind of worked on that project. And that was an example of what's called behavioral cloning. Okay, you would take the car, you would drive it around a track yourself. That would actually generate the data set, the ground truth. And then you'd use a standard supervised model to train the model and then deploy it on the car and race it that way. And that's great. Behavioral cloning works, but it means you only create a model as good as the person driving the car, right? Whereas reinforcement learning, because it's exploring and exploiting, it allows you to potentially be better than the human driver. Anyone familiar with the Dota and the League of Legends games will know that reinforcement learning took on the champions and beat them soundly by creating unheard of and unseen moves before. Okay, and that's the reason. Okay, is that the reinforcement agent can explore every single possibility, something that humans typically won't do. Okay, and that's why reinforcement learning has an advantage over behavioral cloning. So we've talked a little bit about the reward function, and actually I kind of love Lyndon's picture better than this one, but this one is relevant because it talks about the Cobra Effect, which I think sometime in India, the English government that was running there wanted to try and tackle a problem with cobras. Okay, they were killing a lot of people, so they introduced a bounty. We'll give you some money if you bring in a dead cobra. Okay. So what happened was, in the short term, they did a good job. The amount of cobras decreased, and they had less of a problem. But then what happened? Suddenly, people got wise to this, started breeding cobras as a revenue stream. Okay, and they realised that this was not a bad idea. They killed the bounty, and then the people who had been breeding them let all these cobras go, and now they were like 3 or 4 times more cobras than they were in the first place. So the point of that is beware of your intention versus your incentive. Okay, you might think this is the greatest reward function and it's going to do this. And as I think, is that a picture of your son? Was it on that? No, okay, yeah. So, they will find a way round, okay, unexpectedly. So it's really important to think about that, your incentive and what actually that incentive is actually making happen. So now we're going to talk a little bit about how this kind of works. There's a couple of animations here that kind of like try and break this down in kind of an animation way. So we're taking a very simplistic kind of like plan. We've got the agent, which is the car, and in this instance, the goal is just to get to the finish line. Okay, it's a straight track. It's not complicated, but the car can go forward, left, and right. And when it's moving, okay, what will happen is that we create a reward function and we incentivize it a certain way. Okay, in this particular one, it's very simplistic. If you go along the center line, you'll get the maximum reward. If you go along the purple one, you die. The episode will get restarted, and anything else gets you a smaller amount of reward. Okay, so what will happen? Okay, is an episode will kick off, and so that episode again from the start to when it falls off the track or completes it will generate a reward. In this instance, the reward is 2 + 2 + 0.2. Okay, and that will happen. We'll do lots of iterations. Every iteration will generate a different reward. Okay. And then we do this repeatedly. This is what training is, okay? And what we'll see is that the reinforcement algorithm and the DeepRacer will start to understand, okay, if I do it this way versus that way, I get higher reward. And so the idea is you want to, over time, as you have more episodes, see an upwards trend in the total cumulative reward. And you can see here that it's now beginning to kind of finish the race. But as you can see, it's not really the optimum path, yeah? You can see that it can do much better than that. And that's what you're going to find, okay? You will find as you're doing this, you can get round the track, okay? You can get round in 20, 30 seconds, but it's not the optimum time. Other people are going to do it much quicker, so therefore, it means you've got to go back to the drawing board, you've got to create a new reward function, tune those parameters, and find a better way, a faster way of getting there, okay? And ultimately, what you want to be doing is, just to go back, so the left-hand side, the exploration mode, is when you first start. You can see it just looks like it's randomly going off everywhere. And very soon after, it collects data and starts training, you'll see on the right-hand side it actually looks much more smooth. So my driving's on the left-hand side, and probably your driving's on the right-hand side. And then, the kind of the process of building training data, training the model, redeploying that onto the virtual car, and repeating will happen over time until you get this upward trend and what we call convergence, which is where your model really isn't improving anymore. Okay, so you've got to the point where it's got as good as it can get, and obviously what you're looking for is that straight line there, and that we now know for this particular one is Converge. So let's talk about the virtual simulator. So from an architecture perspective, these are the kind of AWS services that are typically under the covers that you don't see, we hide from you, but are being used in DeepRacer. So we've got a robotics tool that's based on ROS, Gazebo, RViz, which is the virtual piece of this. We've got then SageMaker, which is used for the actual training, and then the supporting services. There's Redis actually is missing on there. S3, Kinesis video streams, CloudWatch, and Redis are used to basically put data through those different components and kind of like make it all work. From a workflow perspective, you start with creating the model on the left-hand side. Number one, there are 3 things you can do. As I mentioned, you create your action space. That's really important because you can't change the action space once you've created it. You can change your reward function and high parameters once you've trained and retrained again, but you can't change the action space. So you need to think about what your action space is going to be for your particular approach. So once you configure training, you then train. Okay, and I'm going to walk you through the console. You can train from 5 minutes to 8 hours. And once you've trained the model, you will know whether this looks like a good model, whether you want to tweak it and retrain what's called cloning, or whether you want to ditch it and start again. But if you think you're quite confidently got a good model, you can then evaluate it using the evaluate option. And what it will do is it will submit it to 3 or 5 laps, 3, 4 or 5 laps against the track, and then you will see how well it does against those. And based on that, if you want to, you can then deploy it on the car, or you can submit that to the virtual league as well. And then if you want to tweak it and adjust it, you can then go through that loop again. Again, the only thing you can't change at that point is the action space. If you want to change the action space, then you need to restart from scratch. Okay, so that's kind of the workflow. Okay, I've got these on screen. I think what I might do is I might just go straight into the console and show you this actually happening, because it'll probably be more interesting for you guys. So whilst I'm doing that, are there any questions that you guys have got on the second part there?
How many courses are there?
Well, you'll see. There's I can't remember how many number-wise, but there's about 7, 8, I think.
Tracks.
How many tracks? Yeah.
Does like the total, like the maximum amount of convergence you have, is that the same for every course?
So the convergence is on the model. It's not on a course, right? So you deploy the agent, okay, into an environment. The environment is the track. You can change that. So whether it has an impact, that's a good one. I mean,
So you might converge on one track, but if you go to another track, you might still get some improvements because there's new characteristics.
I wasn't sure if it's based on the track or the robot as well.
But the track is just a way of giving feedback to the model to learn. So if you just use one track, that model will do relatively well on that track, but it might not do so well on other tracks. So to get a utopian model, you do want to try to raise some different tracks and train on different tracks, and then it becomes more deployable. But then that comes back to tactics. You have to slow down so that it becomes a bit more generic.
so advanced section after me. Make sure you stay around for that, okay? Thomas is a killer, so he's very good at explaining that. So when you go into to find the DeepRacer console, you just type in DeepRacer here, because we've got too many services. It's hard to find them all. So DeepRacer. This is currently only available in North Virginia, so make sure you're in North Virginia. And when you get onto that, what will happen is you will get to this screen here. You can click on Get Started, and I've already done this, okay, but you'll get a thing here saying Create Resources. And so the first thing you need to do is do that, and it'll set up some of the IAM and permissions required to do this. Now, if you did this a while ago when it first started and left it and have come back, you need to delete your stuff and reset it, because we've made some changes and you'll be running on the old architecture. So it's really important, if you have done this in the past, to reset this. Okay, there'll be an option here saying reset resources. Do that before you start. Okay, but most likely, if you haven't done it before, then that you won't need to worry about that. You just click on Create Resources. It's an orange box. It'll take probably about 5 minutes, and then you'll be ready to go. And then you can literally click on Create Model. Okay, so what the first thing you need to do on Create Model is give it a name. So we'll do this Meetup number 3. And here is where you actually see tracks. Okay, so these are all the tracks you can, okay, learn. Now, I would not recommend learning on the advanced tracks yet, as tempting as it might be. I would stick to the reInvent one for a number of reasons. First of all, most of the content help that's out there exists on this track. So you're more likely to be able to read and understand stuff people have written based on that. The second thing is that it's actually much more simple from the point of view of when you're using some of the advanced tools to sort of debug. Okay, so stick with the basic one first. As you get more ambitious, more adventurous, then start exploring the other tracks. So once we've got that out of the way, we then have the action space. Okay, so again, what is the action space? Who can tell me what the action space is? Kind of. What else? It's what the agent can do, right? It's what the agent. This is when you're thinking about the neural network. Okay, you've got the input, you've got the layers within the CNN, and then you've got the output. Okay, the output of the convolutional neural network, that output is the action space, right? So it's a discrete action space. So that's why you can't change it, right? So that's why in this instance, okay, these are some defaults, but I can change it from 3 to 7. I mean, I can have a really simple action space, right, of like just 3 things, right? So go left, go right, go straight forward at 1 meter per second. I've got a feeling this isn't going to do great, right? Who knows though? It might. Or I could whack it all the way to the top, We've now expanded this to 12. And now I've got an action space that's quite large. So the ramifications of that, because it's very tempting to go for that, right? Lovely control, lots of options, my car's going to be fantastic. But what do you think the ramifications of having a bigger action space is going to be? It's going to be longer to train, yeah. Maybe not necessarily difficult, but it's going to take longer time to train, right? So that's why, based on your strategy, which Thomas will probably talk about afterwards, you need to think about what makes sense for you. If you've got a track that's just a straight line, you don't need a complicated action space, right? If you've got a more intricate track, then maybe a better action space makes sense. Then we have the reward function. This is where the magic happens. And this is where you need to get your fellow deep racers drunk and try and steal their secrets. Okay, so obviously Lyndon at the back there. He's already had a few beers, so I reckon he's ready now for spilling the beans. We provide 3 examples. Okay, so here's the first one, which is follow the center line, stay inside the 2 borders, and prevent zigzag. Okay, now these are pretty straightforward. You can click on use code, and then you click on validate. It makes sure that it works. So you can't go wrong, okay? If you try and put something in there it doesn't like, click on validate. If it goes red, you start again.
Just a question. So you're not working with raw camera data, you're working with stuff that you extracted from the camera.
So we're working with data parameters, we call them, that you get given in the environment. So actually this is probably a good reward for click on info. And we've got a whole bunch of stuff that we have access. I've got it in the presentation. I'll come back to that in the presentation because I think the presentation's got a nice animation. It shows you how this works. But effectively, within the reward space, you've got a bunch of environmentally variables from the virtual environment that you can use to help the reward function. So things like waypoints. Where am I based on the waypoints of the track? Are all the wheels on the track or not? The yaw of the steering, the speed I'm going, how far have I progressed around the lap. All these variables are available to you in your reward function. It's Python. You can't get away. So if you don't like Python, learn it, okay? Because you can't do anything else at the moment. But once it's trained, at that point the model's finished. When it goes to the real car, if it's on the real car, in fact, even on the evaluation, that's not used anymore. Yeah. Correct. It does the inference, so that the camera is then used to inference against the model. Yeah.
Where does the Python run?
The Python runs. That's a good question, actually. I've never been asked that before.
The Python runs at the back of RoboMaker.
Yes, it does. That's right.
Each time the car completes an episode, which is once around the track or once crashing, it executes the reward function for each step to see how much reward the car would have got for that step. So at the end of the training, it collects all those sample points and then says, based on that picture I saw at the time, I took this action, I got that reward. Did that behave as I expected or not? And then it learns from that over time. So Python runs during training.
So the car contains neural network.
Yep.
The car does its thing in the Convergence episode. Then you run, or the data, the log function, the log of the training is run through the reward function, updates the net neural network, and then you run it again.
So every n episodes, it pauses and changes all the weightings of the neural network based upon how much learning rate
Yeah.
you applied to that, and then it improves if it can improve.
Yeah. And that is done not on the car. It's done on the SageMaker.
Yes. But the state space itself, that is something that can be loaded into the car, that I suppose, because it identifies what
Yes, the car is a way for the action space,
Yeah.
not the state space.
Yeah.
And that will then control the motors and things for the actual steering.
But the action space is actually the only thing that you change directly in the car. The neural network is
You don't change the action space. The action space you define at the beginning, and that's the output of the neural network.
Yeah, but what I mean to say is, if you take the car and you look at what can you change in the car itself, you change the action space because you make
Yeah, so the things that you learn with the car are the neural network and the action space. So and the two go together. So when it says output one of the neural network doesn't know what that actually is. It's the action space that
start your
No, you don't change the action
No.
space.
No, you don't.
You
So
change that to train. And then when you train a new model, you download a combination of what the action space was that you trained with and the model, and that gets complemented.
the physical car can map to the action space, okay, which is what it's constrained by what you can do. So you can only steer so much left, so much right, and when you create the action space, that's then mapped onto the car when you deploy it. So what in the physical car, the car is running OpenVINO as its inference engine, and it has a camera. So when it gets the first image in, it will run that image through OpenVINO against the model you've created, and that will then basically map it to an action space. The action space which you defined will then take the servo, make the servo go so much this far, or the motor go that fast. That's how it works, right? Right. So once you've done the reward function, okay, which is where you'll probably spend the most of your time. During the training, you've then got options to tune the hyperparameters. Okay, I'm not going to cover that in this session because that's more advanced. The default ones are going to be okay when you first start, but you will definitely need to dive deep and explore these in order to optimize the training. Okay, and Thomas might cover that in the next session. And then the final bit here is actually how long you train the model for. So I'm going to leave the default. You can go from 5 minutes to 8 hours. And then you click on start training, and that's it. I've now started my first DeepRacer model. Okay. Now what's going to happen in the background? It's now provisioning all those services, and you're going to see in a few moments the stuff come up on the screen. It will now start training that over the next, in this instance, 60 minutes. Okay. And what you can do is you can actually track kind of a very loose level through a graph that's going to come up. I can actually show you what it looks like in some of the other models. So here, so you can see here. There's actually that's not a particularly good one. Let's see if I can find a nice one. Nope, that's an even worse one. Let's have a look. I've got one that's actually here we go. It's a bit of that one. So you can see here that from when I started training, okay, so we've got two lines, a blue line and a purple line. Let's have a look. The reward is the blue line. So this is the maximum amount of reward. As you can see, as time goes on, my reward is going up to a point where it begins to plateau up here. And then the other one, the purple line, the blue, is it the blue? Purple. Yeah, so the purple line is actually how far it's progressed around the lap. Okay, so obviously from the beginning it's not getting round to the lap at all, but once you get to 100% hit, it's now getting past and going round successfully every single time. So what you really want to see is that upward trend, but be careful, this is not a particularly useful tool to do deep dive analysis of how good or bad your model is. This is only indicative that you're getting slightly better and it's going round the lap. What you really need to do is invest the time and effort into do the log analysis, which obviously Thomas is going to talk to you about after me, and it's definitely worth diving deep in that. So let's see if that's actually now started. So you can now see that the service is kicked off. That's the bird's eye view of the virtual camera in the virtual car. Okay. If we look at RoboMaker, so we can have a look at RoboMaker, and it's spun up a environment, and we can see have we got anyone here who's into robotics? A few? Okay, right. So you definitely want to check out this service. You can see now at the moment it's just still prepping everything, but that is the virtual car on a virtual environment, which is what's used to actually test and get the data to put into SageMaker to train. And what will happen is you'll see this move. I'm not sure if we'll see it now, but at the moment it's still prepping everything. The car will start moving. It will move very erratically. And then what will happen is that as there's a thing called an experience buffer. Experience buffer is a collection of the data that it's got. It will train that through SageMaker and then redeploy that. So what you'll see is it will move, and then every now and then it will pause for a bit. And that pause is where that training is happening. The updated model is being put back onto the car, and then it kicks off again. All right. So if you see it paused, that's what it's doing. So we'll come back to that. So I'm going to go back to the deck and finish it because we've kind of cracking on time, and I want to get Thomas down here. Come on. Right. Okay. So we've talked about the action space. We've talked about the reward function. And now we talk about the parameters. So these are the parameters that are available to you in your reward function. Okay, so I'm going to just show you some animations to kind of build these, bring these to life a little bit. So one of them is the heading, and you can see here that as the car's going around, how that's changing. So you can use that parameter in your Python reward function. Waypoints, which seems to be very popular. I'm not going to say any more than that. But waypoints are your friends, and you can see how they relate. And then we've got are all the wheels on the track. Now, if you think about it, you know, if you're doing the racing line, do all your wheels really need to be on the track? Probably not. And then we've got distance from the sensor. So you can see how all of these values can be used within your Python function. You assign them a variable, and then you do something. You associate a reward, bearing in mind the Cobra effect. Bearing in mind, is it going to do what you think it's going to do? We've talked about the hyperparameters. I think you, Linda, talked about the learning rate. Was it the weighted? The learning rate, which is how big the weights are when you're doing the training, how big those adjustments are. We've also got the entropy, which is the amount of exploration versus exploitation. But Thomas will probably go into some of these as well. But you will dive deep into these as you start getting more experience. So I've done the first bit, and I think that's pretty much what I wanted to cover, really. I'm just conscious of time because I want to bring Thomas down. Are there any burning questions that people have got? Okay, good question. Thank you. So when you create DeepRacer to begin with, I think you have enough for 10 hours training, I think, approximately.
So you get $30 free.
Yeah. And it's about,
which notionally is 10 hours. But
yeah.
It may not be exactly.
Yeah, it depends on how good you are. But I mean, I think my advice would be definitely make sure you set up alarms on your billing. You keep an eye on it for sure. However, I'm going to close my ears because you've got the community has created a great solution for this.
Yeah, so two things, right? So in terms of actually getting a winning model, so my London Summit model that we did place had 8 hours of training in total. But that's obviously knowing the perfect path to the training, which of course you're not going to get. So that's one of the main reasons that in May, quite a lot of us spent a lot of money on DeepRacer. And so come June, there was a big drive in the community to do something about that. So what we've actually done is we've actually taken the whole DeepRacer tech stack and formed it to run on any essentially local machine, so at least the CPU, ideally the GPU, and which is running free. So we now run 24/7 for free. And you can upload those models to Converge to your car without any charge. That's it. Some people don't have a good GPU local machine, or they have customers to buy one. And so people have actually taken that and running it on EC2. And when you run it that way on EC2, which is a bit more of a headache, and to be fair, you will learn a lot more around Docker and a whole bunch of services you probably never wanted to learn about, but it's a good learning exercise in its own way. And running on EC2 is about a tenth of the price of running it through the console.
Yeah.
It's great.
And you can use things like spot instances as well.
Yeah, you can do some of that.
So you can really reduce your cost. And I think that a lot of people have done it, have learned so much about it, they've actually helped them get better models. Yeah. Yeah.
So back to my wife, in the first month I spent $700.
Yeah. So I think I always advise people to make sure you keep an eye on the bill because we don't want that to happen.
All this information that's available on the channels?
On the community, yeah.
Yeah, so in the community we have a channel dedicated to local setup, because it's the number one question we get asked. And there's since the first May environment that we put together, other people then have wrapped it for dummies. So admittedly, it was not completely pain-free. There's a lot more pain-free. It took me about 3 days of effort to get it set up first time around. Now you run it through scripts and it gets it set up for you in the process. So yeah, if you join the community, you will automatically be added to that channel because I've set it up that way. Yeah. And ask away. But there's a whole bunch of documentation online as well. So
Yeah. It's very cool. It's very, very cool.
And just when it's learning, does it learn in real time? Does it learn at accelerated
Oh,
time?
interesting question. So in the AWS stack, it runs in real time because there's infinite-ish compute available. It doesn't need to. So in my local training, it really depends upon the speed of actually your CPU rather than GPU. So mine runs at about 0.9 real time, which actually is good because when I upload it, it runs faster. So actually, the real-time factor doesn't matter too much. And there are people in the community who are speculating, why can't we run it in double, triple time? It doesn't take much more processing power, and it will cut your costs even further.
Yeah.
We haven't quite nailed that yet in the process, but that's certainly doable.
But that's why having a community do that together, it makes sense, right? You can all learn and do that together and pitch in. I'm going to unclip myself. I'm going to get Thomas. So is there anyone here who doesn't want to go to the advanced session? If you don't want to come with me now, I'm going to go back upstairs. If you want to stay here for Thomas, I recommend it. Then stay where you are.
What's more fun, upstairs or here?
I think you'll learn a lot more with Thomas, and the stuff with the log analysis itself is worth the price of admission.
In honesty, we will